Yeah. So we'll start with the continuous time Fourier series. So the continuous time Fourier series, we use it to calculate the Fourier series of the periodic signal. Okay. So this we don't use it for a periodic signal. This continuous time Fourier series is applicable only for the periodic signal. So if you have any signal, let's say x of t, which is a periodic signal, which means that it is satisfying the criteria that it is able to repeat itself for every capital T, where capital T is the time period or fundamental time period, and its angular fundamental frequency is 2 pi by capital T. Then in that case, the signal xt can be represented with the help of this Fourier series expansion. So xt will be equal to the c of k e to the power j k omega naught t, and some where k is varying from infinity to minus infinity to infinity. And here the omega naught t is angular fundamental frequency. Okay. Now this ck is what we call it as a Fourier coefficient. Okay, Fourier series coefficient, and this ck you can calculate it by this formula. So ck is equal to 1 by capital T, where capital T is the time period, and integrate it from 0 to capital T xt e to the power minus j k omega naught t. Okay, so here we have a positive sign in e power j k omega naught t. Here we have the negative sign. So this sign you have to remember. And here the integration that you are doing it from 0 to capital T, you can do it from minus t by 2 to capital T by 2 also. So you can choose any time period window, okay, over the time period. So you can take any time t and you can integrate to t plus capital T. Okay, so this time difference has to be time period, but it doesn't need to be only from 0 to capital T. It can be, let's say, minus t by 2 to plus capital T by 2, or some other number, let's say t to 2t, 3 to 2t to 3t, and so on. Okay, so you can choose any time duration which is equal to the time period of the signal. So this is how we calculate the Fourier coefficient C of k. Now here the C of k is generally a complex number, which means that it will have the real part and it will have the imaginary part. Now this is C of k, if you put the different value of k, you'll get the different value of the Fourier coefficient. Okay. So first term, which is a C of 1 or C of minus 1, this two term we call it as a fundamental tone of xt. Okay, fundamental term. Then if you take any other thing, let's say ck, or let's say c2 c minus 2, or c3 c minus 3, this we call it as a, so this one we will call it as a second harmonic, and this one we will call it as a third harmonic. There is nothing like first harmonic. We call it as a fundamental term, not the first harmonic, just a fundamental term. So harmonic thing will start from the second harmonic, third harmonic, and so on. Okay. Here you will get one more value that we call it as a C of 0. Okay, C of 0. This C of 0, we call it as a DC term, or we also call it as an average. Okay, it is also known as the average. Okay, so it is both DC as well as the average. So if you put k equal to 0 here, when you put k equal to 0 here, the C0 will be given as 1 by t, 0 to t, xt dt. Okay, once you put k equal to 0, this term will become 1 and you will reach here. Okay, you see, essentially what we are doing here is we are integrating it from 0 to t and then dividing it by 1 by t. So that means that we are calculating the average of the x of t. That's why we call it as average, and it is also known as a DC term. Anyone has any doubt?
One thing,
Yeah.
sir, actually, from where did this formula originated? This x of t equal to sigma k equal to minus infinity to infinity. On
Okay,
what page?
so I will not derive it, I will say it analytically. So for every time domain signal, there will be correspondingly frequency domain signal, and frequency domain signal tell us about the uh, behavior of the signal in frequency domain. Okay, so let's say if I say that my signal is varying from, let's say, somewhere around 20 hertz to 20 kilohertz. For example, our voice signal varies from 20 hertz to 20 kilohertz. So that means that that represents the frequency of the signal. Okay, so this frequency means that how rapidly is the signal changing. Okay, how the signal is changing with respect to time, and if the signal is changing very rapidly, it means that signal has the high frequency content, and if signal is changing slowly, that means that signal has the low frequency content. Okay, now let's come to this Fourier series. So in the Fourier series, this Fourier series we calculate only for the periodic signal. For example, we have the signal x of t, which has a periodicity of, let's say, 2 year. Okay, if you see the bottom of the signal, it is a periodic signal with period capital T equal to 2. Okay, now here when we are going to calculate the Fourier component of this signal, so it should be something like a frequency. When we add all those frequency, it should be still a periodic signal. Okay, it's so let's say I have a x of t and I am adding all the frequency content. Okay, let's say e j omega 1t plus, this is what we call it as a fun, like a basic eigen function, right? So this xt will be kind of a summation of lot of this term m omega 2t, j omega 3t, and so on. Okay, xt will be kind of like this. Now, and there will be some weightage here, let's say some a1, a2, and so on. Okay, when you add all this to, you will be getting this x of t, and this e to the power j omega 1t is telling that we have a content of the signal at omega 1 frequency, and its strength is a1. We have a signal at omega 2, strength is a2, and we have a signal at omega 3, strength is a3, and so on. Okay, now when you add all this signal, we will still want it to be periodic signal. Okay, and that will happen only when this omega 1, omega 2, or omega 3 is kind of the integer multiple of the omega naught. Okay, which is the fundamental frequency of the xt. Okay, that's why this signal x of t will have only the frequency content which is integer multiple of omega naught, like omega naught, 2 omega naught, 3 omega naught, and so on. Okay, so that's where this Fourier series comes into picture. Okay.
Okay.
Yeah.
Thanks.
So let's take the example. So this is the one of the periodic signal, and we want to calculate its Fourier series. So when you calculate the Fourier series, you need to just, so here I am taking the integration from 0 to capital T, which is the this point to this point. Okay, now during this point, the signal has this function e to the power minus 2t. Okay, this is changing like e to the power minus 2t from t equal to 0 to t equal to 2. Okay, so I will use this x of t here and put it here. So e to the power minus 2t, e to the power minus j k pi t. Here omega naught will be given as 2 pi by capital T, and capital T is equal to 2. So which means that omega naught is pi. So this is replaced by pi here. Okay. Now let's put it here. So you'll get 1 by 2, 0 to 2 e to the power minus 2 plus j k pi t. Now once you integrate it, you will get this term, and this is the limit 0 to 2. Now once you put the limit for t equal to 0 limit, you will get 1, and for t equal to 2 limit, you will get this term. Okay. Now, if you see that for lower limit, I put the positive, for upper limit, I put the negative sign because there is already a negative sign here. Because of that, I have changed the order here. Okay. Now, if you see this term, e to the power minus j k 2 pi, you can write it as a cos k 2 pi plus, or you can write minus j sine 2k pi. Okay, now this term is equal to 1 and this term is equal to 0. Okay, so you can directly write that this term is equal to 1. So you will be left with 1 minus e to the power minus 4 and divided by 2 plus 2 jk pi. Now if you see this c of k, it is a complex number. It means that it has a real part and imaginary part. Okay. Now since it has a real part and imaginary part, so when you calculate ck can also be written in the form of magnitude and the phase of the c of k. Okay, where the magnitude will be given by under root real part square plus imaginary part square, and the phase will be given as tan inverse imaginary part divided by real part. A typical way, the way we represent the polar coordinate kind of way. Okay, so you have the complex number. Through that complex number, you can find out what is the magnitude part of that complex number and what is the phase part of that complex number. Okay. So this ck can be represented with the help of magnitude and the phase. Let me go to the next slide. Now, problem is asked in the one of the IS problems. So here we have a complex exponential representation of the Fourier series, and we have a signal x of t which is equal to del t minus b summation, where b is varying from minus infinity to infinity. We need to find out what is the value of a of k. Okay. Now, first thing is that if you see this signal, this is a periodic signal. Okay, this is periodic signal. So if you plot it, it is how it is going to look like. You have so when you put b is equal to 0, you will simply get delta t. When you put b equal to 1, you'll get delta t minus 1. When you put b equal to 2, you'll get delta t minus 2, delta t minus 3, and so on. Okay, so you will be getting kind of impulse train. You have one impulse here, one impulse, one impulse. So this is all for the positive value of b. For the negative value of b, for example, if you put b equal to minus 1, you'll get delta t plus 1. When you put b equal to minus 2, you'll get delta t plus 2, and so on. So you'll get some impulse on the same impulse on the negative time also. Okay. So this is the time axis. And for t equal to 0, t equal to 1, 2, 3, and so on, we are getting this impulse, and then similarly minus 1, minus 2, minus 3, minus 4. It will continue till minus infinity, and on the right side, it will continue till infinity. Okay. Now, if you see this signal, this is a periodic signal with period capital T is equal to 1. Okay. Now, in this case, if you calculate the A of k will be pretty easy. So 1 by capital T minus t by 2 to t by 2 x of t e to the power minus j k omega naught t dt. T is equal to 1, so 1 by 1 minus 1 by 2 to plus 1 by 2. Now, from this minus 1 by 2 to plus 1 by 2, the signal is essentially equal to delta t. So I will just write it as a delta t e to the power minus j k omega naught t dt. Okay. Now I will use the property of the delta t. So once I use the property of the delta t, you can think of this second signal as a x of t. Okay, or instead of x of t, let me write as a g of t, let's say. So g of t multiplied by delta of t, it will become g of 0 delta of 0 t, right? So g of 0, which means that I need to replace this t with 0, and this complete thing will become exponential to the power 0, and you will be left with minus 1 by 2 to plus 1 by 2 delta t dt. Okay, and finally this integration will be equal to 1. So ak is always equal to 1. Okay, so this will be the correct answer. Anyone has any doubt here?
No doubt.
Okay, let me go to the next slide. Okay, now here the question is asked in the different way. Here we already have the c of k. We need to find out what is the x of t. Okay, so x of t is given as summation k equal to minus infinity to infinity. Okay, k equal to minus infinity to infinity c of k e to the power j k omega naught t. Okay, now here C of k is given, we need to find out what is the x of t. So it will become k equal to minus infinity to infinity. Now this C of k you can replace with this thing, okay? So you have a j delta k minus 2, delta k plus 2, and then delta k minus 3 and delta k plus 3, okay? So minus j delta k minus 2 plus j delta k plus 2 plus delta k minus 3 and then 2 delta k plus 3, and this thing is getting multiplied by e to the power j k, and omega naught value is pi, so you can write pi t, okay? Now here you are multiplying delta k minus 2 with this thing, okay? So what you will do, you will replace this k with 2 here, right? This property that delta k minus 2 into e to the power j k pi t, okay? It will result. So this is actually the discrete, okay? This is not the continuous kind of function. This is a kind of discrete function, okay? So when you multiply this with this function, you will simply get, when you have to replace this k with 2 e to the power 2 pi t, okay, into j. So you will get minus j e to the power j 2 pi t. Similarly for this one, the second one, you'll get plus j e to the power minus j 2 pi t, okay? For the third one, this is plus minus 3, so you'll get plus e to the power j 3 pi t, and the fourth one will give you 2 e to the power j 3 pi t, okay? So this will be the final xt that we will get, okay? You can combine them also. So if you combine this two, you'll get the sine term, and if you combine this two, again you will get cos term with some phase multiplication here. So this one you can write it as a j minus j common e to the power j 2 pi t minus e to the power minus j 2 pi t. Now you can divide it by 2j and multiply it by 2j, okay? So if you see this term, this is essentially a sine, okay? This is sine, and here you can take e to the power j, wait, yeah, here you have a, okay, this is minus, this will be minus here, e to the power minus j 3 pi t divided by 2, and you can do multiplied by 2, but after that also you will be left with one more term e to the power minus j 3 pi t. We will leave it as it is. Now you can write it as a, so you have a j into j square, which is minus 1. This minus, that minus will cancel out each other. You will get simply 2 sine 2 pi t, and for this one you'll get 2 sine 3 pi t, and this one you'll leave it as it is, e to the power minus j 3 pi. So this will be the signal x of t.
So that's cos, right?
Wait, yeah, this is cos. The third one, sorry, second one is cos. This one is cos pi t. Yeah. So this is the time domain signal that we'll get. Let me go to the next slide. Now let's say we have been given a signal which is like this, and
So
for this
one second,
yeah. Okay.
just take it note. Okay, thank you, sir. Thank you, sir.
Yeah. So let's say we have this signal, and for this signal we want to find the ck. So there is a two way to find the ck. One is to use the formula of the ck, and there is a, whenever you see this kind of signal where you have some constant plus some sine, cos, this kind of term, instead of going through that method where we use the ck equal to 1 by t and then all those integration, what you can do is you just find out what is the fundamental time period here, or what is the fundamental frequency here. So once you find out that what is the fundamental frequency, so in this case when you calculate you will get omega naught, okay? That will be the fundamental frequency. Once you have this fundamental frequency, just expand all this sine and cos into their exponential formula. Okay, so sine omega naught t, you can write it like this. Cos omega naught t, you can write it like this. And this cos 2 omega naught t plus pi by 4, you can write it like this. Okay, after writing this, wherever you see e to the power j omega naught t, just take all of them common. So here we have this one and this one. Take this two common. So e to the power j omega naught t, when you take two common, you'll get 1 plus 1 by 2j. Now let's take e to the power minus j to j omega naught t common. So you'll get 1 minus 1 by 2j, this term. Now let's take e to the power j 2 omega naught t common. So this is the only term. And this is for the e to the power minus 2 omega naught t. Okay. Now, after having this, you just compare it with this Fourier series formula that we have. Okay. Now, if you see this Fourier series, when you put k equal to 1, you are going to get this exponential, and this term, which is 1 plus 1 by 2j, is going to be your C1. Okay. When you again compare this with this term you will get when you put k equal to minus 1 here. It means that the term which is multiplication of this exponential is c minus 1. Okay, so this term is c of 1, this term is c of minus 1. If similarly this term is c of 2 and this term is c of minus 2. Okay, and then we have a term which don't have any kind of exponential, and that is our c of 0. Okay, so this is a c of 0. Now other than this thing, we don't have any other term. That means that c of 3, c of 4, or c of minus 3, minus 4, minus 5, or c of 5, all of those are 0. Okay, so we don't need to calculate those. Now based on this observation, we can simply write that c of 0 is 1, c of 1 is 1 minus j by 2. I have just modified it here. Then c of minus 1 is 1 plus j by 2. C of 2 is this, which is you just expand this e to the power j pi by 4. You will get this term, and this is the c of minus 2. So this is this. Okay. Now, if you are asked to find out what is the c of 3 here, so c of 3 will be 0. Similarly, c of minus 3 will be 0. C of 4 will also be 0, and so on. All those terms will be 0. Now, in this case, if you see this all this coefficient, they are complex number. So you can try to represent this complex number with the help of the phase and the magnitude. Okay. So when you take the magnitude of the first one, which is c of 0, you'll get magnitude is simply equal to 1. And when you calculate the phase of c of 0, it will be 0 because it doesn't have any imaginary term. When you take the second one, c of 1, when you calculate the magnitude, you just take the under root real part square and the imaginary part square. That will be the magnitude. And the phase, you just need to do tan inverse imaginary part divided by real part. Okay. So this is the magnitude at k equal to 0. This is the magnitude at k equal to 1. Similarly, this is the magnitude at k equal to 2. You can plot it, and this is what we call it as a magnitude spectrum. This is the magnitude spectrum. Okay. Similarly, you can plot the phase also. So phase for k equal to 0, we got 0. K equal to 1, we will get some negative value. K equal to 2, we will get some positive value, and so on. Similarly, for the k equal to minus 1, you'll get some positive value. And k equal to minus 2, you'll get some negative value. So this plot, we call it as a phase spectrum. Okay, phase spectrum.
Sir,
Yeah.
sir, in XT there is two term is there having same fundamental frequency, so we should write in a common sign term, na, will be magnitude 1 upon root 5. I mean root 5 will be the magnitude in that case.
But it will have the phase also, right? It won't be just magnitude modification. Correct?
No sir, like sine omega naught t plus 2 cos omega naught t, and write in
Yeah, yeah.
root 5 of sine of omega naught t plus something of phase. of that thing?
Yeah, the phase term will also be there, right? It won't be like just a simply root 5 as a magnitude. Yeah,
Yes, sir. Some phase part also be there.
yeah, some
That
phase
phase
part.
is coming in the same coming at in the C1 and C minus 1. Actually, I'm that asking.
So yeah, so it is something like that only. So if you see this sine omega naught t into cos omega naught t, so your cos omega naught t term is giving the this one, and the sine omega naught t term is giving you this minus j by 2, correct? This minus j by 2 is coming from the sine and the plus 1 is coming from the cos. And when we are calculating the phase, we are just dividing it this two. Okay, so it is essentially coming from this. But the thing is here is that when you do those root 5 and like when you can calculate it like this. I got your point. So you're telling that we can write it like r1 and sine, wait. We can write it as r into cos omega naught t plus theta, right? Something like this form we can write by combining
Yes, sir.
these two, correct?
Yes, sir.
Yeah, but that will not serve any purpose, right? Finally, we need to find out what is the C1 and C minus 1. I mean, you can do the I like that and then finally arrive at this result only, but that will not serve any purpose.
Okay, means this thing also gave the same result, no?
Yeah, that will also give the same result.
Okay, sir. Okay.
Anyone has any other doubt? Okay, let me go to the next slide then. So the Fourier series expansion that we just saw till now, that we call it as exponential expansion, because here xt is given in the form of exponential, which is ck e to the power j k omega naught t, okay, where k is varying from minus infinity to infinity. You will find some place that this Fourier series can also be written in the form of cos and sine. This we call it as a trigonometric Fourier series representation. And there is no difference between the this signal and this signal. Only the difference is the representation. Here the representation in the form of exponential. Here the representation in the form of cos and sine. The reason is that we can move from this exponential to cos and sine because is this exponential is essentially a cos and sine, right? You can write this e to the power j k omega naught t equal to cos k omega naught t plus j sine k omega naught t. Okay. From there, once you can also write this thing in the form of cos and sine. This we call it as a trigonometric Fourier series. Now this a naught is same as c naught. Okay, that is the DC term, and then we have a ak and the bk. Here, these two are the Fourier series component, ak and bk. Now, a naught is same as c naught. So if you see this formula, this is same as c naught. Here the formula for the ak and bk will be slightly different. So ak will be given as 2 by t capital T 0 to capital T xt and cos k omega naught t dt. And for bk, it will be sine k omega naught t dt. Okay. Now there is some relationship between the c and a and b. First thing we already know, this is c naught is equal to a naught. Now the second thing is this, ak will be equal to ck plus c minus k. Okay. So how is it coming is that, let me write this. So xt is equal to summation of ck, and exponential we can write it as a cos k omega naught t plus j sine k omega naught t. Okay. Now you can also write it as a c0 plus summation ck let me write it into different form. minus k. Okay. Give me a second. Okay, and j sin omega naught t. Okay, yeah, I got the point. So here it will be c0 plus summation k equal to minus infinity to infinity ck cos k omega naught t plus again ck into j sin k omega naught t. Okay. This thing you can divide it into two parts. Here k is varying from minus infinity to infinity, except at k equal to 0. For k equal to 0, I've taken out this c of 0. Okay. Now here, when you add this, you can also write it as a c0 plus summation k equal to 0 to infinity, not 0, 1 to infinity. 1 to infinity c of k cos k omega naught t plus summation k equal to minus 1 to infinity ck cos k omega naught t. I'm not writing the sine term. I will just leave it for I will just writing the cos term here as of now, and we'll see what is the relationship for the ak and ck. Now if you see this, here we have a k equal to 1 to infinity, here we have k equal to minus infinity to minus 1. Now here this cos is a kind of a even function of k, okay, but ck we don't know what is the function of the ck here, whether it's even or odd, we don't know. So we will just use a general function here for the ck, but for cos we know that it is even function. Okay, so you can write it as a c0 plus summation k equal to 1 to infinity c of k cos k omega naught t plus, you can take the negative sign from this k, the summation, and put it here inside the k. So you can write it as a k equal to 1 to infinity c of minus k, and then cos minus k omega naught t. But I will just write as a cos k omega naught t, because cos is even function of the k, and because of that, whether it's the minus k or the plus k doesn't matter. Okay. Now you see both this term, the first term and the second term, both has a limit from k equal to 1 to infinity, so you can combine this two. Okay, once you combine this two, you'll get ck plus c minus k, which is essentially equal to ak if you compare this equation with this one. Okay, so that's where you'll get ak equal to ck plus c minus k. Similarly, if you do the same thing for the sine, you'll get bk equal to jck minus c minus k. Okay, and ck you can write in terms of ak plus jbk. So this is the relationship between the trigonometric Fourier series and the exponential Fourier series representation. Anyone has any doubt here?
So one two factor will be also coming in the last equation.
This
Uh,
sign, you mean?
ck equal to ak minus jbk by 2 is coming or not?
No, 2 won't come, right? There is a node 2. So if you see this ak, if you compare this equation with this equation, so here in the coefficient of cos k omega naught t, we have a c of k and we have a c of minus k, right? And here the coefficient of cos k omega naught t, we have ak. So that both of them has to be equal if you compare this equation with this, and that's why ak will be equal to ck plus c minus k.
Okay.
I
Is
think
it clear?
so. I
Yes, sir.
think because of using the Euler's formula, it got confused, I guess.
Oh no. So here we have just replaced this with this and put it here, right?
Yes, yes. So no issue.
Yeah. After that, we have I have written cos in two form. One is from negative value of the k, and one is for positive value. So this is the positive value of the k. This is the negative value of the k. And for 0, I have just separated it out. This is C0. Okay. And then after writing this, instead of putting the negative value of the k in the limit, what I have done is I have replaced this negative value and put, instead of k, I put minus k here itself in the ck and the cos k omega naught t. So instead of ck, it has become c of minus k, and instead of cos k omega naught t, it will become cos minus k omega naught t. But cos minus a is same as cos of a, right? Cos is even function of this argument, and because of that I have not put the minus sign here. I've just written as a cos k omega naught t. Okay. Now this complete thing you can write it as a c0 plus summation k equal to 1 to infinity ck plus c minus k cos k omega naught t, correct? Now if you compare this equation with the top one, this one, you'll see that here we have a cos omega naught t, here also we have cos k omega naught t. Limit is from 1 to infinity, limit here is also from 1 to infinity. Here we have coefficient ak, here we have coefficient ck plus c minus k, and that's why ak should be equal to ck plus c minus k. Okay. Now is it clear?
Yes, sir. But sir, in last equation, I think 1 by 2 factor is also coming, na? Like ck equal to ak minus jbk by
Okay,
2.
this one, let me check. ak minus jbk, when you do,
Yes, sir. A minus jbk equal to 2 ck is coming.
yeah, there will be 2, yeah, correct. So 2 ck is equal to this one, yeah.
Sir.
Yeah, this is the correct one. Yeah. Anyone else has any doubt? Let me go to the next slide. So again, I will just quickly go through the property. This is very similar to what we have seen for the Laplace and the jet transform. First is the linearity property. So you have two signal xt and yt, both has the same time period capital T. Their coefficient is c xk and c yk, and you do the linear combination and you will get the resulted signal ZT, which has also same time period capital T. So the coefficient of this ZT will be again linear combination of this two coefficient. Okay. Next is the time shifting. So if you have a signal x of t, its Fourier coefficient is c of x. For this xt minus t naught, the Fourier coefficient will be given as, actually this will be c of k, e to the power minus jk omega naught t naught ck. Again, it is same for the Laplace also. When you do the time shifting, you multiply it with e to the power minus st. Okay, the same thing has happened here. Next is the time reversal. So let's say you have a signal x of t and its Fourier coefficient is c of k. Okay, so xt you can write it like this. Now let's say you want to calculate the Fourier coefficient for this one. Okay, x of minus t, and here let's say this is the Fourier series of that. Okay, and let's put the k equal to minus m here. So once you replace k with minus m, here it will become m equal to infinity to minus infinity. Instead of k, it will be c minus m and e to the power j m omega naught t. Okay, this one I have just extended the limit here. Okay, this one finally you will get this one. So if you see this one and compare it with this one, okay, here the coefficient has the different sign. Here it is ck, here it is c minus m, and that means that when you do the time reversal here, your coefficient will become also kind of reversal in the k domain. Okay, now here let's say you have a signal which is an even signal. Okay, so if xt is an even signal, x of t will be equal to x of minus t. For x of t we have a coefficient c of k, and for x of t, x of minus t, we have a coefficient c of minus k, And since these two signals are equal, then in that case, these two will also be equal. Okay. Similarly, if you have odd signal, so in that case, you have x of t is equal to minus x of minus t, and its coefficient, this Fourier coefficient of this signal is c of k, and Fourier coefficient of this one is c of minus k. In that case, ck will be equal to minus c of minus k. Okay. So this is an important property. We'll further explore this in the one more property that we'll see later on. Okay. So whenever the signal is even, its Fourier coefficient will be even function of k. Whenever the signal is odd, its Fourier coefficient will be odd function of k. Let me go to the next slide. So let's say we have a signal x of t and its fundamental time period is capital T and its Fourier series coefficient is x of k. Okay, it is same as what we have been seeing as a ck. Okay, ck is here xk. Now we need to find out what will be the Fourier series coefficient of this signal. Okay, so here we have a x of t and t minus t naught and x of t plus t naught, and we need to find out what will be the Fourier coefficient of this. So here we need to use the property of the time shifting. So if you have a signal x of t, its Fourier coefficient is ck. Then if you have a signal x of t minus t naught, the Fourier coefficient of this signal will be ck multiplied by e to the power minus j k omega naught t naught. Okay, so this will be the Fourier coefficient of this x of t minus t naught. We have x of t plus t naught. So for this one, the Fourier coefficient will be c of k e to the power j k omega naught t naught. Okay. Now, after that, we are adding this two signal. So here we will apply the linearity property. If you add the two periodic signal with same time period, the resulted signal will also be periodic, and the Fourier coefficient will be having the same linear combination as we have in the time domain. So the Fourier coefficient will be xc of k e to the power j k omega naught t naught plus c of k e to the power minus j k omega naught t naught. Okay. Now we can take the c of k common, and you can write it as e to the power j k omega naught t naught plus e to the power minus j k omega naught t naught. You can divide it by 2 and multiply it also by 2. Now this will be the cos, so you can write it as a 2ck cos k omega naught t naught, where omega naught is equal to 2 pi by capital T. Okay, so you can write it as a 2ck cos k 2 pi by capital T into t naught. Okay, now here I have written as it as a c of k. In the question you can replace it with x of k. So here you can replace the c of k with x of k. Okay. So in this problem, this will be the correct answer. Anyone has any doubt here? Let me go to the next slide then. Now the next property is the time scaling property. So if you have a signal x of t, its Fourier coefficient is c of k, and you're doing the time scaling of the signal. Okay, so let's say you have a x of et after the time scaling. Okay, now one important thing here to note is that when you do the time scaling of the signal will still be a periodic signal, but its time period is going to change. Okay, so for example, let's say you have a signal which is cos omega naught t, which is x of t. Now let's say I am going to scale it by factor of 3, x of 3t. So you'll get cos 3 omega naught t. Okay. So in the first case, the time period is t equal to 2 pi by omega naught. In the second case, the time period will be t equal to 2 pi by 3 omega naught. Okay. So the signal will still be a periodic signal, but the time period is going to change by the factor at which we are doing the time scaling. So let's say we have a signal and we are doing the time scaling by factor of a. In that case, the time period will be t by a. Okay. Now for this new signal, the Fourier series will be given as summation k equal to minus infinity to infinity. Okay. C of k, x of j k omega naught at. What I have done, I have taken this equation and I have just replaced a t with at. So this t will become at. On the right side also this t will become this a of t. Okay. Now if you see this, if you compare this equation with the typical Fourier series of formula, you will see that the Fourier coefficient is not going to change. Only this time period is changing. The new time period will be equal to 2 pi by a into omega naught. Okay. Earlier it was 2 pi by just omega naught. Now it is 2 pi by a into omega naught, which is means that new time period is getting scaled by factor of a. And that is captured here. The new frequency is now a into omega naught. Okay. So old angular frequency was omega naught. Now it is a into omega naught. If you compare this with the typical Fourier series, the ck is still there in the place. Nothing has changed in the ck. That means that the Fourier series coefficient is not going to change with the time scaling. Only the time period is going to change. Okay. So an example is this. So let's say you have a signal x of t. It is equal to sine 2 pi t. So when you calculate its Fourier series, you just expand it into the exponential, and this exponential will give you the c1 and c of minus 1. Okay. So the first term is e to the power j2 pi t, which correspond to k equal to 1, and the second term is e to the power minus j2 pi t, which correspond to k equal to minus 1. Now let's say you are scaling it by a factor of 2t. So in that case, you will get sine 4 pi t, and again we are going to expand it. Okay. Now, when I'm going to expand it, I am going to compare it with summation of ck e to the power j k 4 pi t. Okay. So earlier for the upper case, I was going to compare it with summation of ck e to the power j 2 pi kt, because at that time omega naught was 2 pi. Now in this case omega naught is 4 pi, so I'm going to compare it with this. So once I compare it with this one, c of 1 will be again same as upper one, and c of minus 1 is again same as the uppercase. Okay. So when you do the time scaling, the Fourier coefficient ck is not going to change. Anyone has any doubt?
Sir, it's written like Fourier coefficient hasn't changed, but Fourier series representation hasn't changed.
So Fourier series representation has changed, just this term has changed, this one. So this ck has remained intact, only this one has changed.
But in the slide, it is written both hasn't changed.
Okay, actually, okay, yeah, this term should not be there. This one, it has also changed. So coefficient hasn't changed, but okay, this has changed actually. It should be has, yeah.
Okay.
Yeah. And let me go to next slide. Okay, this is very important property. So if you have so this property will be used a lot. Okay, this we will be seeing in the Fourier transform also, the same property. So this is the conjugate and conjugate symmetry property. So let's say you have a signal x of t, its Fourier coefficient is c of k, and let's say you are taking the conjugate of the signal x of t, and for that you are getting the Fourier coefficient. It will be equal to c of minus k conjugate. Okay. Now, I'm not going to derive this one, but let's see what happens when the signal is real signal and signal is real plus even and real plus odd, all those scenario. Okay. So let's me take the case when the signal is a real signal. In that case, x of t will be equal to x of conjugate t. Okay. So in that case, these two things will be equal. Now that's because of this, the C of k and C of minus k conjugate, both of them will be equal. Okay, or you can say that C of k conjugate is equal to C of minus k. Okay, so from here to here, on the both left and right side, I have taken the again conjugate of the both of them. So C of k conjugate will be equal to C of minus k. Okay. Now we know that C of k is a complex number, so it can be written in the form of magnitude and a phase. Okay, so this is the magnitude term, this is the phase term. Okay, now when you take the conjugate of the C of k, the magnitude term is not going to change because it's a magnitude, but the phase term is going to change. It will become e to the power minus j phi of k. Okay, now when you calculate the C of minus k, you just replace k with minus k, so it will become C of minus k e to the power j phi of minus k. Okay, now for the real signal, this C conjugate and C of minus k both are same. So it means that this term and this term will be equal. Okay, so which means that C mod of C of k e to the power minus j phi k is same as mod of C of minus k e to the power j phi minus k. Now since these two are equal, it means that this magnitude and this magnitude should be same, and this phase and this phase should be same. So which means that C of k should be equal to C of minus k, and phi of k should be equal to, so minus phi of k, minus phi of k should be equal to phi of minus k. Okay, so here whenever the signal is real signal, its magnitude spectrum is even function of k, because when you do the minus k and plus k, they are same, but the phase term is odd function of k. Okay, so the magnitude spectrum is even function of k, and the odd phase spectrum is odd function of k. Okay, so for all the kind of real signal, magnitude spectrum will always be the even function of k, and the phase spectrum will always be the odd function of k. Anyone has any doubt here? Okay, let me go to the next slide then. Now let's take a case when the signal is real as well as even. Okay, now from the case when the signal is real, we know that C of k conjugate is same as C of minus k, and from the signal is even, we know that C of k should be equal to C of minus k, right? This one we have derived few slides back. Okay, now from this two thing, you can write that, so from this equation and this equation, you can write that C of k conjugate should be equal to C of k. Correct? From this two equation, you can write that C of k conjugate should be equal to C of k. So when the signal is real as well as even, in that case, C of k will always be a real and even. Okay, so whenever you have a signal which is a real as well as even, its Fourier series coefficient will also be a real and even. The second case is when the signal is real and odd. In that, when the signal is real, we know that this is the thing, and for the when the signal is odd, this is the case. Okay, from this two equation, you can write that C of k conjugate will be equal to minus C of k. Okay, and this thing will happen only when ck is purely imaginary, it doesn't have any real part. Okay, so whenever you take the conjugate of any imaginary part, it will become a negative of itself. Okay, so when the signal is odd and real, then in that case the Fourier coefficient will be purely imaginary. Okay, so when the signal is real plus even, the Fourier coefficient will always be real plus even, and when the signal is odd, the Fourier coefficient will be purely imaginary. Okay. Now, in general, signal can be a not perfectly even or odd. It can be kind of mix of real plus, sorry, even plus odd signal. So in those cases, so let me just explain this. So let's say you have a signal x of t and it has some even part and it has some odd part. Okay. Now when you calculate the Fourier series of x of t, and from there you got the Fourier coefficient c of k. Okay, this is the c of k, which is a complex number. In general, it will be a complex number. It means that it will have a real part, it will have an imaginary part. Now you are getting a real part because it has some even portion, and you are getting imaginary part because it has some odd portion. So this even part is responsible for the real part of the CK, and this imaginary part is responsible for the, sorry, this odd part is responsible for the imaginary part of the CK. Okay. So if the signal is perfectly real and even, then it will be, its Fourier coefficient will be real and even. And if the signal is real plus odd, in that case, the Fourier series coefficient will be purely imaginary. But in general, signal may not be perfectly even or odd. It will be kind of combination of the real plus odd signal, sorry, even plus odd signal. So in that case, when you calculate the Fourier series coefficient, it will be CK and it will be a complex number. Since it is a complex number, it will have a real part and it will have the imaginary part. You're getting the imaginary part which correspond to the odd portion of the signal. You're getting the real part which correspond to the even portion of the signal. Is this point clear to everyone? Okay. Then I will go to the next slide. Okay, this is one of the highest problem. So let's say you have a signal which is a periodic signal, and this is the Fourier series expansion. If the signal x of t is a real and odd signal, then the Fourier series coefficient are. Okay. So here we need to use a property that we just discussed in the last slide. In the problem, it is given that it is real and odd. Okay. So since this is real and odd, its Fourier series coefficient will be imaginary. Okay. Anyone has any doubt? Let me go to the next slide then. Next is the Parseval's theorem. So Parseval's theorem is all about to calculate the power in the Fourier series domain. So let's say you have a signal which is x of t. So we know that for the periodic signal, this is how we calculate the power. This power can be calculated into the Fourier domain also. So this is how we calculate the power, summation of k equal to minus infinity to infinity ck square. Or if the this signal is represented in the trigonometric Fourier series representation, then this is the way you can calculate the power. So this is for the exponential representation. This is for the trigonometric representation. Okay. Next is the differentiation in the time domain. So when you differentiate in the time domain, you will be multiplying it with jk omega naught. It is very similar to again the Laplace transform. There we were multiplying it with s. Next slide. Okay, this one we have just discussed in the few slides back. So if the signal is perfectly, let me just sign it. Okay. So if the signal is not perfectly even or odd signal, it can be written like this, and its Fourier coefficient is c of k. C of k will have a real part and an imaginary part. Real part is getting because of the even portion, and you're getting imaginary part because of the odd portion. Now I have a problem here. So let's say we have a signal x of t, which is equal to e to the power j omega naught t. And here we need to find out what is the c of k. Okay. Now this is very simple problem. You just need to compare this xt with summation e to the power ck e to the power jk omega naught t k equal to minus infinity to infinity. When you compare this equation with this one, you will see that only for k equal to 1, you have a ck. For rest of the value of k, it is 0. Okay. So in this case, ck will be, c1 will be equal to 1. Okay, you don't have any other term here. Let me go to the next slide then. Now, this is again an important topic for the Fourier series. This is what we call it the half-wave symmetry. So any signal which is satisfying this criteria, okay, which means that when you shift the signal by half of the time period, you will get the negative of the same signal. Okay, and signal xt is a real signal. If this two criteria is satisfied, in that case, we call this kind of signal as a half-wave symmetric signal. And it has an important property that for this kind of half-wave symmetric signal, ck will be equal to 0 for odd value of k. Okay, ck will be there only for the even value of the k. Okay, so when you have a signal which is satisfying this half-wave symmetry criteria, in that case ck will be equal to 0 for all the odd value of the k. Okay, sorry. Here there's a mistake here. It should not be odd. It should be even actually. This will be even. So ck should be equal to 0 for the even value of the k. Now, after this half-wave symmetry, there is a something called the quarter wave symmetry. Okay. So what is the quarter wave symmetry? Let's say you have a signal which is a half-wave symmetry. So let's say you have a half-wave symmetry signal plus it is even. Okay. So we call this as a even quarter wave symmetry. Okay. Now here we have a two thing. First thing is that signal is half wave. Second thing is that signal is even. Okay. Now when the signal is half wave, we know that ck will be equal to 0 for even k. Okay. And since the signal is even, in this case, when you calculate the Fourier series, you are going to get only the cos term. Okay, why we are going to get only the cos term? Because signal is even, and if you see the Fourier series expansion of the trigonometric Fourier series, you have a cos term and you have a sine term, and we know that the sine term is odd function of t and the cos term is even function of t. So whenever you have a signal which is even signal, it will not have any odd term. It will have only the even term, which is cos here. Okay. And because of that, if the signal is half wave symmetry and even, it will have the ck only for the odd value of k. For the even value of k, it will be 0. So it means that only odd term are left. And in the odd term also, you don't have any sine term. You have only the cos term. Okay. So if any signal is even plus half wave symmetry, it will have only the cos term, and the cos term will have only the odd harmonic. It will not have the even harmonic. Okay. So if this signal is even quarter wave symmetry, it will be having the cos term and only the odd harmonic. Okay. Now the second kind of signal is when the signal is half wave plus odd signal. In that case, we call it as an odd quarter wave. Okay. Now in this case, since the signal is odd, it will have only the sine term. It won't have any cos term because cos is even function of t. And since it is a half wave, it will have only the ck only for odd value of k. For even value of k, it will be 0. Okay. So it means that for the odd and quarter wave signal, you will get only the sine term, and those sine term will only be there for the odd harmonic. There won't be even harmonic. Okay. Anyone has any doubt in this half wave symmetry and the quarter wave symmetry? Okay. Let me go to the next slide then. Okay. So I have shown one example here. So the first signal, if you see this signal is odd signal. Okay. If you see this, whatever is there is positive for the positive time. For the negative time, for negative of that time, it will be negative. It is having the negative value. Okay. So it is the odd signal, which means that it is satisfying the x of t is equal to x of minus t. And if you see this signal carefully, this is satisfying the half wave symmetry also, because if you take this signal and shift it by half of the time period, it is going to become the negative of the x of t. Okay. So this is satisfying the half wave symmetry plus odd. Okay. And since it is half wave symmetry plus odd, it will have only the sine term. It won't have any cos term. And since it is going to have only sine term, it will be having only the b of k. A of k will always be 0. And since it is half wave symmetry, even though the b of k we have, it won't be there for all the k. It will be there only for the odd value of k. For even value of k, bk will be equal to 0. Now if you see the second signal is even signal. Okay, it is satisfying this criteria that x of t is equal to x of minus t. And also this signal is satisfying this half wave symmetry criteria, that if you shift it by half of the time period, it will become negative of the time. Now because of this two property, that it is half wave symmetry as well as it is even signal. Here, because of the even signal, we will not get any b of k. All the b of k will be 0. Only we will get a of k. And whatever the a of k we are getting, we will be getting only for the odd value of the k. For the even value of k, a of k will be 0 because of the half wave symmetry. Anyone has any doubt here? Let me go to the next slide. Okay, so we have a question here. We have been given this signal, and for this signal, we need to find out which of these four options is true. So first option is it has both sine and cosine term. It has only sine term. It has only cosine term. It has only, I think it should be odd term. I think this option is wrong, I guess. We can just remove it. So here, if you see this signal is even function of t. Since this signal is even function of t, this signal will not have any sine term. It will have only the cos term. Okay, so it will have only the ak cos k omega naught t, this term only. It will not have the pk sine k omega naught t term. Okay, this term will be 0. Only we will have this term. And because of that, this option is correct, that it will have only the cosine term. It won't have any sine term, and it won't have both sine and cosine term. So anyone has any doubt till this point of the Fourier series? Now we will start a new topic, that is the Fourier transform. So the Fourier series that we saw till now, we use it only for the periodic signal. If the signal is aperiodic, we won't be able to use the Fourier transform. Sorry, Fourier series. This Fourier transform, we can find it for the both periodic as well as the aperiodic signal. Okay, there is no restriction with respect to the periodicity for the Fourier transform. We can calculate it for both aperiodic and periodic signal. So this Fourier series we calculated by this formula. Now if you see this formula, this is same as what we saw in the Laplace transform with s equal to j omega. If you replace the s with j omega, the Laplace transform formula becomes the Fourier transform. Okay, and we have the inverse Fourier transform formula also. So x of t is equal to 1 upon 2 pi minus infinity to infinity x of omega e to power j omega t d omega. Now in some book, you'll see this formula also. Minus infinity to infinity x of f e to power j 2 pi ft dt. You won't see 1 by 2 pi term here because here d of omega is getting replaced by d of f, and omega is equal to 2 pi f, and because of that this 2 pi is getting cancelled by this 2 pi. So d of omega will be equal to 2 pi df. So this 2 pi and this 2 pi get cancelled and you get just this thing. Okay, so some book you will see this kind of formula, some book you will see this kind of formula. I will be going with this formula most of the time. So let's say here we want to calculate the Fourier transform of this signal, okay, where a is greater than 0. Now unlike the Laplace transform, here we don't have any kind of ROC concept. The Laplace transform, we had the concept of ROC, and we used to make the Laplace transform converged. In this case, we don't have any kind of ROC criteria, ROC thing here, and because of that, some of the Fourier transform will not converge here. Okay, so we'll see those cases soon. So let's say we have a signal which is equal to e to the power minus at ut, and for this we want to calculate the Fourier transform. Okay, so to calculate the Fourier transform, you will put this signal here and calculate it. Okay, so once you calculate it, you will get this number. Okay, 1 by a plus j omega. Now if you see this now, this thing, it is a complex number. This is a complex term, and since this is a complex, it is going to have the magnitude term and it is going to have the phase term. Okay, so when you have the magnitude term, so this is how this is the magnitude term, and you can plot it, and that plot we call it as a magnitude spectra, just like we saw it for the Fourier series. It had the magnitude spectrum and the phase spectrum. In the similar way, for the Fourier transform also, we can calculate the magnitude spectrum and the phase spectrum. Okay, so this is the magnitude, this is the phase. This magnitude and the phase spectrum, you can plot it with respect to omega. So this is the magnitude spectrum of this a 1 by a plus j omega, and this is the phase spectrum of the same Fourier transform. Okay, here if you see this phase, this phase will be like if you put omega equal to plus a, its phase will be equal to minus tan inverse a by a, which will be equal to minus pi by 4. Okay, that's what it is written here. At a, it will be minus pi by 4. And similarly, if you increase the value of omega, it will go towards the minus 90 degree, or you can say minus pi by 2 also. So this is the phase spectrum, and this is the magnitude spectrum. Okay. Anyone has any doubt here? Okay. Go to the next slide then. So now let's say this is very important signal. This signal is like in the lot of problem, you'll see this rectangular pulse based problem for the Fourier transform. So let's say we have a signal which looks like this. And for this particular signal, we want to calculate what will be the Fourier transform. Okay. So for this case, you can use again the Fourier transform formula to calculate it. So it will be equal to minus infinity to infinity x of t e to the power minus j omega t dt. Okay. Now in this case, x of t is equal to capital A from minus t to t. So you can write it as a minus t to capital T a e to the power minus j omega t dt. This you can also write as a e to the power minus j omega t divided by minus j omega, and limit is changing from minus t to capital T. Okay. Now once you put the limit, you will get a e to the power minus j omega capital T minus e to the power j omega capital T divided by minus j omega. Okay. This you can further write it as a e to the power j omega capital T minus e to the power minus j omega capital T divided by 2j into 2 divided by omega. Okay. I have done some rearrangement here. So after that I am getting this one, and you can write it as a sine omega capital T into 2a divided by omega. Okay. Now this one you can also write it as a capital T division and capital T multiplication. This thing we call it as a sinc function. Okay. Sin x by x form, sin x divided by x. It is in this form. This we call it as a sinc. So it is equal to 2at sinc of omega capital T. Okay. So this is the Fourier transform of this rectangular pulse. It's better to remember this. So how to remember it? So what we do is, here if you see this 280, this 280 is equal to area of this rectangular pulse. Okay, area. So if you calculate the area, it will be equal to 280 and then sinc of omega t. So this is how I try to remember it. I just put the area term and then sine omega t by omega t, okay, where this capital T is the half of this window. So this total window is 2t, half of the window will be t. Let me go to the next slide. So this problem that you see in the screen, this one is just directly based on the problem that we saw in the last slide. So we have we want to find the how the Fourier transform of the rectangular pulse signal which has a duration. So here we have a rectangular pulse which looks like this. It is there from minus t by 2 to capital T by 2. And for this one, we want to calculate what will be the Fourier transform. So just now we saw that the Fourier transform of the rectangular pulse will be sinc function. Okay, it will be sinc function. So here it will be this option. So if you remember this Fourier transform, you don't need to calculate it in the exam to find out whether it's a sinc or sine or cosine. If you just remember this one Fourier transform, you can say that this is the answer. This will be the sinc function. Now I will just quickly go through the few property of the sinc function. So if you have a rectangular pulse minus t to capital T with height a, we know that the Fourier transform we just calculated is this one, sine omega capital T divided by omega capital T. Now when you are going to plot this with respect to omega, okay, you're going to get a peak at omega equal to 0. At omega equal to 0, it will have the maximum value. Then since it is a sine, it will be going down, up, down, like this. And its amplitude is kind of shrinking with omega. And the reason is the denominator, as you increase the omega, this complete thing is going to go down. Okay. So this height is going to be more than this one, or this height is going to be less than this one. It will continue to shrink in the height. Okay. Now the maximum value that you see here, it is equal to 2 capital A capital T. At omega equal to 0, this term will be equal to 1 and you will be left with 2A capital T. Okay, now you see it is crossing the 0 at some frequency. Now what is this frequency at which it is crossing 0? So this complete thing will be equal to 0 when sine omega t is equal to 0, and this will happen at sine n pi. For integer value of the pi, integer multiple of the pi, this sine n pi is generally 0. So you can say that omega capital T is equal to n pi. So omega is equal to n pi by capital T. Okay. So for n equal to 1, it will be pi by t. N equal to 2, 2 pi by t. N equal to 3, 3 pi by t. And it will continue. Similarly on the negative time, minus pi by t minus 2 pi by t and so on. So this is the Fourier series, Fourier transform of this rectangular pulse, and this is the how the x of omega looks like in the plot. Okay. Now one thing to note here is that in this case, this x of omega is perfectly real. It doesn't have any imaginary part. Okay. The reason is that our signal x of t is real plus even. Okay, the signal is real plus even, and because of that the x of omega is real plus even. Okay, it doesn't have any, since it is real, it will not have any phase term, or in other word you can say that its phase is always equal to 0. That's why it doesn't have any phase term. Okay. Anyone has any doubt till this point? Okay. Slide. Okay. So we want, in this problem, we want to calculate what will be the Fourier transform of the impulse. Okay. So this is going to be pretty easy. So this is the Fourier transform formula. Just replace this xt with impulse. Okay. Now I'm going to use property that gt into delta t is equal to g of 0 into delta t. So this will become minus infinity to infinity delta t dt, because this term will become a g0, which is equal to 1. Once you do this integration, you'll get equal to 1. So the the Fourier transform of the impulse is equal to 1. Let me go to the next slide. Now again, the similar property, we will again quickly go through it. So if it is signal is a linear combination of two different signal, then its Fourier transform will also be the same linear combination. Time shifting, if you do the time shifting in the frequency domain, it will be multiplication by e to the power j omega t naught. If you differentiate it in the time domain, it will be multiplication by j of omega in the Laplace transform, which was multiplied by s. Now integration in time domain is slightly kind of different than the Laplace. When you do the integration in the time domain, you'll get x of omega divided by j omega, and other than this, you'll get this term also, which is pi x of 0 del of omega. Okay, so this is the other term which we get with respect, as if you compare to the Laplace transform. In the Laplace transform, you'll just get x of s divided by s. There won't be any other term. But in the case of Fourier transform, you are going to get this extra term. Okay. So let me go to the next slide and we'll see one of the problem. So here, let's say we have a signal gt, and if you see this is the Fourier transform of the gt, which is equal to omega e to the power minus 2 omega square. Okay. Now let's say we have a new signal y of t, which is integration of the g of t. Okay. Now for this y of this is the y of t. Now we need to find out what will be the integration of this y of t. Okay. So this is a bit tricky thing here. So to solve this, we are going to use some of the few of the property here. So first thing is note that this yt is integration of the gt. Okay, so here we are going to use this integration property. So what is that integration property? So once you do the integration in the time domain, in the Fourier domain, the Fourier transform of y of omega. So this, let's say this for this y of t, Fourier transform is y of omega. It will be equal to x of omega divided by j of omega plus pi del of omega x of 0. Okay, and in our case this x is actually the gt, so let me replace this x with g. So it will be g of omega and g of 0. Now what is the g of omega? G of omega is equal to omega e to the power minus 2 omega square divided by g of omega, and this term will become 0. Why this term will become 0? Because you have a term g of 0, and this is the g of omega. When you put omega equal to 0 here, this complete term is going to become 0. Okay, so this term is gone, so this term will be completely 0. Now you can write this omega and this omega will cancel out each other, and you will be left with e to the power minus 2 omega square divided by j. Okay, now this is your y of omega. Now y of omega can be written as minus infinity to infinity y of t e to the power minus j omega t dt. Now, when you put omega equal to 0 in this equation, it will become y of 0 equal to minus infinity to infinity y of t dt, which is the thing that we want to calculate here. So essentially, the integration of y of t from minus infinity to infinity is equal to capital Y of 0, which is the Fourier transform of yt at omega equal to 0. So what will be the value? You take this y of omega, put omega equal to 0. So once you put omega equal to 0, you'll get 1 by 8. Yeah, 1 by j. This 1 by j, you can also write it as a minus j. Okay? So this will be the correct answer. Anyone has any doubt here? Okay, we go to the next slide then. Okay. Here, now next property is the time scaling. So when you do the x of t to replace with, so you when you replace this t with at in the frequency domain, this is what is happening. Your omega will become omega by a, and magnitude will get down by factor of a. Okay, so this is the time scaling property. Now this time scaling property, you can extend it to time reversal, just replacing a with minus t. So when you replace this a with minus t, x of, so the Fourier transform of x of minus t will be equal to x of minus omega. Okay. Now the next property is very important property, which is duality property. Okay, and this is a bit confusing property also. So let's check it, see it very clearly. So let's say we have a signal x of t, and its Fourier transform is x of omega. Now let's say we have a signal in the time domain which looks like this x of omega, and let me call that signal as a capital X of t. Okay, so this capital X of t and capital X of omega is a kind of same signal, only the thing is that here it is a function of omega and this is a function of t. So if you have a signal x of t and its Fourier transform is x of omega, and in the time domain you have another signal capital X of t which looks like this capital X of omega, and when you calculate the Fourier transform of this capital X of t, the Fourier transform will be equal to 2 pi x of minus omega. Okay, where x of omega is a kind of same as x of t, only the variable will is different. Okay, in the f domain you can write it different way. X of t is equal to x of Fourier transform is equal to x of f. Then you have another signal which is capital X of t, which is looks like x of f. If you take the Fourier transform, it will be x of minus f. So this is what we call it as a dual property. Let's see what does this dual property mean here. Okay, so we have calculated the Laplace transform of delta t. So the Laplace transform of delta t is equal to 1. Okay, now let's say I want to calculate the Laplace, Fourier transform. So let's say we want to calculate the Fourier transform of 1. So the Fourier transform of delta t is equal to 1, and I want to calculate the Fourier transform of 1. So you can think of this delta t is equal to xt, and this 1 is equal to x of omega. Okay. Now in the time domain also we have, let's say, 1, and for this one we want to calculate what will be the Fourier transform. So if you see this x of omega and if you see this signal, these two are the same signal. Only variable is omega here, here variable is t. It is capital X of t here. Okay. Now for this signal, Fourier transform will be equal to 2 pi x of minus omega. Okay. Here x of t is equal to delta t. So x of omega will be equal to delta of omega. And so x of minus omega will be equal to delta of minus omega. Okay, so you can write this as a 2 pi delta of minus omega, and delta of omega is even function of omega, so you can also write it as a delta of omega. Okay, so based on this dual property we can calculate what will be the Fourier transform of 1. Fourier transform of 1 is equal to 2 pi delta of omega. Anyone has any doubt here? Okay, let me go to the next slide then. Now this question is based on the dual property. So let's say we have a signal which is x of omega equal to del omega minus omega naught. And for this particular signal, we want to find out what is the x of t. It is the inverse Fourier transform based formula. So you can apply the inverse Fourier transform formula, or you can apply the dual property also. Okay. So in this case, first thing is that we know that for delta t, Fourier transform is equal to 1. Okay. Now we have, let's say, new signal delta t minus omega naught. So for this signal, Fourier transform will be equal to e to the power minus j omega naught omega. Okay. It looks a bit confusing, but here we have shifted it by omega naught because I have to come here. Okay, at this point. Now this is the time domain signal, this is the frequency domain signal, this is x of t, this is x of omega. Now when I apply the dual property, in this side it will be 2 pi x of minus omega. On this side it will be capital X of t. Okay. Okay.
So how is that possible?
Tell me again, I didn't get.
How is that possible where delta of t minus omega naught should be t naught, right?
No, here variable is omega naught. So actually it doesn't matter, it's just a constant, right? Whether it's omega naught or t naught, it doesn't matter. it's not a variable, right? It's a constant. That's why you can put omega naught here, and it will look weird here, but it doesn't make any difference.
Like in the one is in time domain and the other
This
is
is
in
not a frequency domain, right? It is just a constant. You can think of some other, let's say, okay, let me just do this. So let me, instead of writing it like this, let me just derive one, and then I will just replace later on with omega naught. So let's say we have a signal delta t, its Fourier transform is 1. Let's say we have a signal delta t minus a, okay? Its Fourier transform is equal to e to the power minus j a omega naught. Sorry, j a omega, just not omega naught. Omega naught will not be there. Okay, so this is the Fourier transform of delta t minus a. I have used the time shifting property here. Now this is x of t, this is x of omega. Now based on dual property, this will become capital X of t, and this will become 2 pi x of minus omega. Okay. Now here this is delta t minus a. If you write it here, it will become 2 pi. So x of t is equal to delta t minus a. So x of omega will become del of omega minus a, and x of minus omega will become del of minus omega minus a. Okay, so I can write this as a del of minus omega minus a. Okay, and in the time domain it will become e to the power minus j a t. Okay, here it is e to the power minus j omega, here it has become e to the power minus j a t. Okay, till this point is it clear? Okay, now if you see this this impulse, you can also write this as a del omega plus a. So del omega plus a and del minus omega minus a doesn't make any difference. Okay, when you plot this del omega plus a, it will be located at minus a, impulse located at minus a. When you plot this, it will be same. There is no difference between these two. So you can write it as a 2 pi delta omega plus a. Okay, so we can say that if you have a signal e to the power minus j a t, its Fourier transform is 2 pi delta omega plus a. Now let's replace this a with minus omega naught here. So 2 pi delta omega minus omega naught. On the left side, it will become e to the power j omega naught t, or delta omega minus omega naught. Its inverse Fourier transform will be 1 by 2 pi e to the power j omega naught t. So this will be the correct answer. Anyone has any doubt? Another way to calculate it through by using the inverse Fourier transform. So that is this x of omega e to the power j omega t dt minus infinity to infinity. You can use this formula also and put this x of omega here, and when you calculate it again, you will get this same value. Let me go to the next slide then. Now next is the differentiation in the omega domain or the frequency domain. It will result in multiplication by minus j t. Next is the shifting in the frequency domain. So when you shift into the frequency domain, it will multiplication by e to the power j omega naught t. So again, this property also you can use in the last slide that we saw. And next is the Parseval's theorem. So this Parseval's theorem is kind of similar to what we see in the Fourier series, but in the Fourier series it was a periodic signal, so it was in terms of the power. Here it is terms of the energy. So let's say you have a signal xt, then energy of that signal xt will be given as this formula, and this same energy you can calculate it to the Fourier domain also. So it will be given by this if you are using the omega as a variable, and it will be given by this if you are using the f as a variable. Okay. So whether you are using the time domain signal or the frequency domain signal, both should have the same energy. Now the problem that you see here, there is a xt sine at by pi t. We need to find out what is the energy of xt. Okay. So when you try to solve this by using this time domain formula to calculate the energy, it will be a very lengthy problem. So what we do is we use the two property here. One is dual property and one is this Parseval's relation to find out the energy. With the help of dual property, we convert this time domain signal into the frequency domain or omega domain. And once we get the omega domain, we use this formula to calculate the energy of the signal. Let me go to the next slide. Now, next is the convolution in the time domain. So it will become multiplication in the frequency domain. Again, same as the Laplace. Now, there is a one extra thing that we didn't see in the Laplace is that when you do the multiplication in the time domain, it will be equal to convolution in the frequency domain. Okay. Next is the conjugate symmetry. It is very similar to what we saw in the Fourier series. So when you have a signal which is a real signal, okay, and its Fourier transform is x of omega, okay, then x of conjugate of omega will be equal to x of minus omega. Okay. Now here this x of omega is a complex thing. Okay, we have seen that this can be a complex number, which means that it will have a real part and imaginary part. And since it has a real part and imaginary part, we can calculate its magnitude spectrum and we can calculate its phase spectrum. Okay, so just like in the Fourier series, we saw that magnitude spectrum is even function of k. Here it will be even function of omega, and the phase spectrum will be the odd function of omega. Okay, we can derive in the same way that we derived it for the ck. Okay. Now let's add some few flavor here. So let's say we have a signal which is real as well as even. Okay. If the signal is real as well as even, in the Fourier series, ck was perfectly real signal. Okay. In this case, this x of omega will be real. There won't be any imaginary part. Now if the signal is real plus odd, in that case this x of omega will be perfectly imaginary. There won't be any real part. So the same property that we saw for the ck is repeating here. Now in general, again, the x of t will be kind of combination of the odd plus even. So when you calculate the Fourier transform, which is a complex number, it will have a real part and the imaginary part. You're getting the real part because of the even component of that signal, and you're getting the imaginary part because of the odd component of the signal. Anyone has any doubt till this point? We go to the next slide then. Wait, I think we can. Okay, a signal is real and odd function, then its Fourier transform f of omega will be. So it is directly based on that property. So if the signal is real plus odd, so the Fourier transform will be imaginary function of omega. Let's go to the next slide. Now Till now, whatever we have seen is the Fourier transform of the aperiodic signal. But as I mentioned at the beginning, the Fourier transform of the periodic signal can also be calculated. So here we know that for any periodic signal, this will be the Fourier series. Okay. Now let's take this and calculate the Fourier transform on both left and right hand of this equation. Okay. So on the left side, you'll get x of omega. On the right side, when you calculate it, this c of k is a constant. It will remain as it is. Now for this term, which is e to the power j k omega naught t, the Fourier transform will be given as 2 pi del omega minus k omega naught. Okay. So this one again we just saw a few slides back. The what will be the inverse Fourier transform of this one? So you can think of this as that it is kind of similar to that one. So this will be the Fourier transform of this. So when you put it here, you'll get this as a Fourier transform. Okay. So when you plot this x of omega, or let's say magnitude of x of omega, here for k equal to 0, you will get some impulse del of omega multiplied by this thing, which is 2 pi c0. Similarly, for k equal to 1, you'll get del omega minus omega naught. So in this case, it will be shifted at omega naught. For k equal to 2, you'll get an impulse at 2 omega naught. And similarly, for k equal to minus 1, you'll get an impulse at minus omega naught, and so on. So for this periodic signal, if you see this Fourier transform, it is kind of discrete in the frequency domain. Okay, in the frequency domain, you see only you are getting only discrete component. It's not a continuous function of omega. Okay, so whenever you have a signal which is a continuous plus aperiodic, okay, in the Fourier domain, you will get aperiodic plus continuous. Okay, and if the signal is continuous plus periodic, in the frequency domain you will get again aperiodic signal, but it will be discrete in nature. Okay, so what you can say here is that whenever the signal is continuous, it in the frequency domain it will always be aperiodic. Okay, so whenever the signal is continuous in the time domain, in the frequency domain, the signal will always be aperiodic. Okay? And whenever the signal is aperiodic in the time domain, so in the time domain, if it is aperiodic, in the frequency domain, it will be continuous. And whenever this time domain signal is periodic, in the frequency domain, it will be discrete. So some of the problem is some generally based on this also. Like I have seen some few previous year problem. They directly ask if the signal is in the time domain signal is continuous and periodic. In the frequency domain, what will be the signal? So in the frequency domain, it will be aperiodic and discrete. Okay? So here you can make the combination. If the signal is continuous and periodic, in the frequency domain, it will be aperiodic and discrete. And if the signal is continuous and aperiodic, signal will be aperiodic and continuous in the frequency domain. So this is the time domain. This is the frequency domain. Okay. Soon we will be seeing the discrete time also. Then this table will be complete with that. Okay. So till now only this thing missing is the discrete time signal here. What will happen to that on the omega domain?
So one doubt, sir.
Yeah.
How can be it aperiodic? Because at equal intervals of omega naught, that means equal intervals of time. That kind of.
No, can you repeat? I didn't get your point.
Like, um, how can the signal be aperiodic? By seeing the figure, if it's equally distributed with omega naught, right? So,
Um, okay, equally distributed. So you mean, let's say I am taking a rectangular pulse in the time domain. In the frequency domain, it is sync, correct?
yes.
So you are saying that it is equally distributed in the sync. Like in the frequency domain, we are getting a lot of component in the frequency domain, right?
Okay, that's a different frequency. Okay. But I have just seen this case as a we are getting the discrete signal is discrete as well as, but as seen in the figure, it's equally distributed between omega naught, right? So, like 0 to omega naught, then omega naught to 2 omega naught. So I had the doubt.
Signal is discrete in the time domain.
No, sir. Like you have just drawn this figure where the output is discrete, but still
Yeah.
the marking is shown as omega naught, then 2 omega naught. That means it's periodic, right, sir?
No. It is not. So okay. So when I say that signal is a periodic, it means that x of omega has to be periodic, not the x of t. But if you see this one x of omega, this is not a periodic signal. I mean, this it will be periodic only if this amplitude that you see it is going to repeat. But for all the value of k, you are getting different value. Like for example, when you put k equal to 1, you are getting del omega minus omega naught and c1, right? You are getting del omega minus omega naught c1. Here you will be getting del omega minus 2 omega naught into c2. Now, if the c1, c2, c3, c4, all those things were same, you can say that x of omega is repeating itself for every omega naught, correct? But in this case, the c1 and c2 may not be same.
Okay. Oh, so I have misunderstood that. Okay, now I got it.
Correct. So this is a kind of discrete, but this height that you see here, they are not same here. Yeah.
Oh,
Anyone else has any doubt? Okay. I think so. Actually, this Fourier series that we calculated it for the x of t, which is a periodic signal, but in the time domain. Okay, this is periodic signal, but we are saying about its periodicity only in the time domain, not in the frequency domain. In frequency domain, this signal is x of omega, and this will be aperiodic. Okay, so in the time domain, it is still periodic signal, but in the not in the frequency domain. For the frequency domain, for it to be periodic, there should be a omega naught which satisfy this criteria. For some omega naught, it should repeat. Okay? It can be any number, but we don't see those number here.
okay.
Next is about the existence of the Fourier transform. So there might be some signal for which we might not be able to calculate the Fourier transform. Okay, so let's say we have a signal x of t, which is satisfying the criteria that it is absolutely integratable. Okay, we can integrate it and find some finite value. Okay, so if the signal is satisfying this criteria, and if the signal is satisfying this criteria that it has only finite number of discontinuity in the finite interval, and it has only finite number of maxima and minima within the finite interval. Okay, so this is the first criteria, this is the second criteria, and this is the third criteria. If these three criteria is satisfied by a particular signal, for that signal, we can definitely find out what will be the Fourier transform. But if the signal is not satisfying any one of this criteria, in that case, we may or may not be able to find out. Okay. In some case, we may be able to find out. In some case, we may not be. Okay. So if the signal is satisfying these three criteria, then the Fourier transform exists. But if signal is not satisfying this criteria, it doesn't mean that Fourier transform will not exist. It means that it may or may not exist. Okay. So one example is the unit step. Okay. Unit step doesn't satisfy the first criteria. Okay. If you integrate it, it will become infinity. Okay. But still, there is an existence of its Fourier transform. Now, on the other hand, if you take the ramp also doesn't satisfy this criteria, and also ramp for ramp signal we cannot calculate the Fourier transform. Okay, so there are some signal which satisfy the which doesn't satisfy the criteria, but still we will be able to calculate, and there are some signal which doesn't satisfy the criteria, and for that we will not be able to calculate. So this condition we call it the Dirichlet condition also. So sometimes they just directly asked based on this property, which of the which of the following criteria should be made to find out the Fourier transform of the signal. Okay, so the question can be asked just directly based on this condition. Anyone has any doubt here? Let me go to the next slide. Okay, so I will stop here. I think it's already 10:30. For rest of the topics, so only topic remaining for the Fourier transform is the steady state analysis and the system response. Okay, so those I will try to finish in the next class. So anyone has any doubt till this point? Okay, so no one has doubt, we will stop the class here. Then in the next class, we will continue this Fourier transform. And after finishing the Fourier transform, we will start the DTFS and DTFT. Okay, thanks everyone.
Thank you very much.